All right, let's talk about some physical optics. We're going to now be just discussing, what is light itself. And the first concept we need to really focus on, which is going to be the underlying concept for the majority of the videos in this unit, is this wave nature of light. What is light? Yeah, is light a wave? Is light a particle? What is it? And I'm telling you, this very question uh, changed science multiple times over the last several hundred years in terms of which scientists believe uh, the truth at the time. And let's kind of take it one step further back. And so, um, far enough back, I want to say it was the 1700s. It may have even been earlier. This fellow named Huygens, which is it's an awkward way to pronounce his name. I'm not even sure I'm pronouncing it right. I don't know if anyone pronounces it right. He talked about light and he kind of described it as a wave. And he said that if we take a wave of light and we look at that wavefront, every point on that wavefront really ends up being a source of a bundle of individual wavelets. And he says these wavelets, these individual, I guess, little bits of wave, spread out in the forward direction at the same speed as the wave. So as a result, these wavelets basically form an overall wavefront. And so if you kind of look at it in this picture here, we've got a bunch of dots here that'll represent the wavelet, right? And they're going to travel forward in unison together to a new location. And so the second blue line is the new wavefront. And so Huygens treated light as a wave, and this arrow that's perpendicular to the wavefront would be treated as a ray. Now you got to understand, it's not like we can look at light. You can't just zoom in. I mean, we look at light, of course, it helps. We see things, but you can't zoom into a light photon or a wave and try to figure out and take a picture of it so we know exactly how it behaves. So this is all theory, and then ensuing years experimentation took place to help confirm whether light is or is not a wave. And so if we were to describe it as a wave, this picture here helps understand what we are referring to when we talk about a ray of light or a wavefront. We have the top view, we've got the blue and the white and the blue and the white and the blue and white. That would be your alternating crests and troughs or your peaks and valleys. If we're looking at the side, we look at it, it looks like a nice transverse wave. And then if we had like a three-dimensional view here, you've got that same transverse wave, their peaks and valleys. And if I were to draw a ray, that ray would be perpendicular to that entire wavefront. It just travels as one unit. All right, so what are some things we can do, or maybe scientists back in the day would do to help postulate whether or not light was a wave or not? Well, one thing is this. If light is a wave, then the question goes, how come light doesn't necessarily behave like other waves? Like, let's take a sound wave, for example, which is a mechanical wave. We know that if we're standing at a location in a room and someone is outside that room and they are speaking, or maybe there's a speaker playing music, we know that as that sound wave enters that opening of the door, it will eventually still get to your ears. You don't need to be in that line of sight to hear the sound. You can be anywhere in this room. It might be quieter or distorted, but you're going to hear that sound no matter where you are. And this is not because of reflection. This is because of this term called diffraction, which is incredibly important to understand for this unit. And there are multiple definitions you can follow, but ultimately it's the bending or the turning of a wave as it enters an opening or an obstacle. And that opening or obstacle needs to be a size similar to the wavelength of the wave itself. So that part's could come into play naturally. Let's take a look at this down here. Really what it means is that wavefront, maybe there are parallel waves entering, maybe it's even a same frequency here, entering this opening. Well, they're going to bend, and now some will head out that way, some part of it will head that way, part of it will head this way, and ultimately there's various different degrees of that bending, but it allows that wave to spread out across the room. Well, light doesn't seem to do that. If we have this is a relatively extreme graphic, but if we have a well-lit room and a dark room, and you're lurking in the corner, you're going to stay hidden back here because that light is not going to fill up that whole room. The whole room doesn't light up. you'll get this shadow. It might be this perfect rectangular shadow, or you might get kind of a little bit of a tapering here, but it's certainly not going to light up the majority of this room. And so light doesn't appear, or at least not in a regular everyday circumstance, does not appear to obey this idea of diffraction, which is limited to waves. So it's curious, right? So naturally, though, this fellow back in the day, Thomas Young, incredibly, insanely important experiment, one of the most famous experiments for physics. You definitely need to know this one for sure. Thomas Young's double-slit experiment. And what Young said was this: if light was a particle, if we were to shine it on two openings that are narrow, relatively the same wavelength or the size of light itself, so these are really tiny openings, or shall I say, these are not only tiny openings, but openings that are really close to each other. He said if light was a particle, as these particles go through these openings, they would just stick almost like a shadow. Not really a shadow, but that's where the line of sight would be, and you would get this nice little pattern. This would be if it was a particle. And he said if light was a wave, when you shine it on these two openings, we'd get a different kind of pattern. And this is a pattern that would be called an interference pattern due to the diffraction of light. And it turns out this is actually what happened. When Thomas Young set up this experiment, he was able to show that as ended up being a monochromatic source of light entering these two openings, you're going to get an interference pattern. And this can only be explained if light were behaving like a wave. If it was behaving like a particle, it wouldn't get that interference pattern. It would simply just not happen. Let's break it down for you in a slightly different graphic, because this is actually what happens. And then the opening needs to be relatively small. Remember, this isn't something that happens with two doors in your, between two classrooms or something. This is going to be a relatively tiny opening, pretty close to itself. And you've got these wave fronts that are parallel to each other. When they hit these openings, they bend, right? And so you might be able to see how we can get interference here, because now we're starting to get one wave front that's propagating forward and taking up 3 dimensions, but we're going to draw it as 2, propagating forward this way, and another wavefront that maybe I'll kind of draw in red. I'm just going to loosely do this to get an idea. Spreading out this way. This is diffraction now, okay? When this red and green get on top of each other, you're going to get interference. Remember, interference, when we have a crest on top of another crest, all right, they add together. We get constructive interference. Or when we have a trough on top of a trough, same thing. But when a crest is on top of a valley or a trough, so when they're on top of each other like this, they're going to get canceling effect. So we get destructive interference. So when you have two identical wavefronts, same frequency, same location of source traveling, you're going to get areas where you're going to get constructive interference, and you're going to get areas where you get destructive interference. And you get this interesting pattern. You can see it, this fading. Well, let's see what it kind of looks like. I'm going to advance forward on this flash simulation here, and if I had a screen here, a photosensitive screen, it would detect bands of light. You'd see bright spots, dark spots, bright spots, dark spots, all the way down the line. And this, again, this is the interference pattern. This would not happen if light were behaving like a particle. If it just traveled forward and didn't diffract or spread outward, you would just get 2 regions, and in fact, those regions would be where most of the dark bands are showing up right now. Instead, you're going to get a diffraction pattern. Another peculiar thing about this diffraction pattern that I find interesting is that you're going to get this bright spot in this dead center location, which is right behind a wall, really. Okay, there's no light directly in front of it, but it's because of the spreading, the way they interfere. And I'm going to try to describe that a little bit better in the next slide. And so if we were to treat it as a water wave, just view it as a water wave, you can probably see how this effect takes place a little bit more. If you've ever been at a pier or any body of water near the shoreline, you're going to start to see this diffraction-like effect as it hits a big boulder, a rock, or part of the pier. That water will bend around it, okay, and you get this more circular style wavefront. And these waves will interact with each other, making bigger waves and shallow flat zones where there's no wave at all, and then big wave, and then a shallow flat zone. And it's a diffraction pattern. Well, we can simulate that with light as well. And so if we were to, I'm going to try to zoom in on this one a little bit better so you can get a better idea of how this interference starts to happen. And also, I want to explain to you that this needs to be a monochromatic source of light. It needs to be light of one frequency. Otherwise, and now don't get me wrong, it will work with white light. You just won't see the white or the bright and dark bands as clearly as we see it here. And to explain what's happening, it's going to be impossible to explain with all kinds of different frequencies of light. So what we're going to do is we're going to first get monochromatic light approaching two openings. And the way Thomas Young and the early scientists were able to do this is they took white light, and that white light would then strike a single opening to try to put them all in phase with each other, basically. And then that light will then be more or less coherent. As it then strikes the two openings, we're going to now get two separate waves coming from it. That isn't as important to understand. Just recognize that this whole setup is one frequency of light approaching two openings, and then we're going to get a diffraction pattern. And from that, we're going to get two wavefronts. As you can probably see, if I were to trace in a few of these arcs in one color and then a few in another color. So perhaps you've got this purple wavefront traveling all the way down to the screen. And then maybe you'll have I'll make it green. Remember, it's the same actual color, okay? It's monochromatic. I'm just making it green to let it pop out in front. So this green one is also traveling down. And you might notice that where the purple ones and the green ones are on top of each other, okay, we're going to start to get a constructive effect. So where they're on top of each other, these black circles that I'm drawing, just to emphasize where they're on top of each other, we're going to get a constructive effect. And so that spreads all the way down until it hits this photosensitive screen, making what we call a maximum. And that's a bright spot. Another term is a bright fringe. It's a term that's used. So there are multiple maxima all the way along, as long as we have the proper geometry to allow for it. But of course, where we have maxima, we're going to also have, not where we have maxima, but if there's maxima, we're also going to have minima. So the maxima occur where the peaks and valleys, where the peaks are on top of each other and the valleys are on top of each other. Well, you're going to get minima where a peak is on top of a valley, so you have a crest on top of a trough. And that's in the in-between zone. It's not as easy to see in this drawing, but trust me, it's there. And so your minima are going to be dark spots. These are going to be locations where it appears no light exists at all, and that's destructive interference. And you do get this nice little pattern. You get this bright, dark, bright, dark, bright, dark, bright, dark, bright pattern. If we were to take a look at an intensity graph of that, we would notice that the center bright band, which is known as the central maximum, if you look over here, it's going to have the greatest amount of intensity. Now, don't think this is actually what it looks like in the wall. This is just an intensity graph, so this is brighter, okay, not taller. And then the next maximum, which would be the first order maximum, or the first order fringe, okay, these guys over here, they're going to be less intense, not as much intensity because light, there's simply not as much light hitting there. And that intensity will taper off as we stretch outwards. So the second order maxima is less intense than the first, and less intense than the central, and all the way down the line. We're going to use M to represent order number because we're going to get these patterns of one bright, another bright, another bright, another bright. So the first order fringe is M equals 1, which means the central fringe, M equals 0. That's going to come into play when we set up our geometry and then eventually our equation. Alright, so let's take a look at the geometry and then eventually set up our math to determine an equation that we can follow. And this might look a little odd. I'm trying to break it down for you step by step, so when we're understanding how interference works, we can see how the patterns work out. So, we've got ourselves a light source. Remember, it's monochromatic, so it's one single frequency, therefore the wavelength is the same. And we're going to treat it as if there are two waves, each entering through each separate hole. But remember, it's really just one source that was then split through these two openings. And so we've got one particular wave of light traveling down until it hits the photosensitive material, or a screen. And then we've got another wave traveling. And since both of these waves entered the opening at the same time, they're both in phase with each other in the very beginning, and they're traveling the exact same distance, they're going to be in phase with each other in the end. Remember, when waves are in phase, you're going to get constructive interference. Because they both traveled equally, you're also going to get the same number of waves, and thus this is why we get the brightest spot here in the middle. Now, if we then try to look at that next maximum, so recall in the middle is the central maxima, then we're going to have another maxima, our first order fringe, on both sides of the center. Let's look at this top one here. I'm going to move that a little bit out of the way. We'll see that the top wave still travels in phase of the bottom wave, but if you count the number of peaks here, it'll have less cycles or fewer cycles that it travels. Now, in order for things to stay in phase, the waves need to be offset by whole increments of a wavelength. So they can be one wavelength apart from each other, two wavelengths apart, three wavelengths apart, etc. And every time there are increments of one whole wavelength apart, you're going to get construction. So as long as the second wave travels one whole extra wavelength or two whole extra wavelengths, you're going to get construction. That's exactly what happens here. This bottom wave will travel a little bit farther than the top wave, and that little bit is exactly one wavelength. That's what we're going to refer to as a path difference. So the path difference between these two waves is one wavelength. Well, if we continue this pattern all the way out to the next fringe, way out here, and way out here, this bottom wave will travel two whole extra wavelengths than the top wave. And so we're going to continue to increase by increments of one whole wavelength. And so for construction, whenever m is equal to 1, 2, 3, or 4, we're going to get multipliers of 1, 2, 3, or 4 times a wavelength. Now when we get to destruction, we want to be out of phase. So destructive is when we're out of phase. And that is where the crest of one is on top of the trough of the other. So they are offset by 1/2 of a wave. So lambda over 2. And you get that effect, again, if we just try to pay attention to the path difference between these two waves, one wave will travel a little bit less of a distance than the other. So the second wave down here, the one that has to travel a little bit farther because it's off center, is going to travel about 1/2 a wave, well, not about, exactly 1/2 a wave longer. So its trough ends up being on top of the other one's peak, canceling out, and so we get dark spots. Well, if you look at this carefully, you're not going to get a dark spot in the center. So this is a dark spot here. This is a dark spot that'll exist down here. And then here's where you're going to get your central maxima. So then you'll get your first maxima on the other sides of each dark spot. And these two are the ones that align with the two that I did over here. And so you find out the path difference for destruction ends up being increments of 1/2 wavelength. But we have to add our whole number to it. M has to be... it'll be treated as m plus 1/2 times lambda, and so you'll get another dark spot again way out here, which would then be 2 plus 1/2, so 2.5 wavelengths, and then you'll get another one, 3.5 wavelengths, 4.5 increments of m plus 1/2. Well, then if we really want to, that's just the path difference between your waves. Let's start to figure out the actual true distance it travels. And so if we kind of break down, let's look at constructive interference for simplicity's sake. If we break down this little area here, that shaded triangle, and try to kind of get rid of the waves so it's a little bit easier to see, we find out that the distance between the two openings, which we're going to treat as d, and then this extra segment is the segment that the one bottom wave traveled. This is 90 degrees here. This is my angle theta here because it's my angle theta here. It turns out that this extra distance that the second wave travels is simply just the hypotenuse times the sine of theta, or d sine theta. And for construction, that d sine theta must equal the path difference, m lambda. And for destruction, that d sine theta must equal the m plus 1/2 lambda path difference. So we get these two equations here. One is specific for construction, and the other is specific for destruction. So you can figure out all sorts of good stuff from this, which we're going to break down in a lab. But specifically speaking, if I know the distance apart from the two openings, if I am able to measure the angle between the distance from the screen and the two bright spots, that's simply using geometry. And I were to do a little bit of rearranging here, I can solve for the wavelength of the light that's causing this interference, or rearrange it. If I knew the wavelength of the light and I knew the distance between the opening, I can predict exactly where my bright spots will land by solving for lambda, or theta. Again, be very clear about these two equations. When it's just d sine theta equals m lambda, it's going to be whole number increments starting at 0. When we're talking about destruction, we're going to do d sine theta equals m plus 1 half lambda. Again, whole number increments starting with 0. So m equals 0 would be half lambda, m equals 1 would be 1.5 lambda, etc., all the way down the line. And one more time, d is the distance between the openings. Theta is the angle between the center line and where the bright spot lands on the screen. M is the actual maxima or minima we're looking at. And then lambda is the wavelength of the source of light that's creating this entire diffraction interference pattern. Alright, that's it for double slit. We're going to get to some more complex scenarios in the future.